All right, today we're diving into something really cool, a brand new framework in the world of pure mathematics that has some seriously bold ambitions. It's called FUC, that stands for Formal Unified Constructs, and its whole goal is to build a new, powerful bridge between what were once completely different worlds of geometry. So let's see how it's supposed to work.
You know, at the very highest levels, math isn't just one single language. It's really more like a continent full of powerful and distinct nations. You've got places like colloid geometry, which looks at really complex shapes. Then you have spinorial analysis and Hodge theory. Now, each of these fields has its own incredibly powerful tools. But here's the thing. They often struggle to communicate. This project is all about building the bridges to connect them.
So you might be asking, why even bother? Why was this unification so necessary in the first place? Well, it really all comes down to a fundamental problem of translation between these different mathematical worlds.
So FUC is trying to connect three pretty distinct traditions. First, you have spin geometry. Think of it as dealing with these really subtle, almost quantum-like properties of shapes. Then there's mixed Hodge theory, which is just a powerhouse of algebraic tools for dissecting complex structures. And finally, you have ramified coverings, which studies how you can map, stretch, and fold spaces. The issue is that each was its own world, and there was just no single, coherent language to describe how they all interact.
Now, the biggest troublemaker in this whole story is something called ramification. Here's a simple way to think about it. Imagine you take a piece of paper and you fold it. That sharp crease, the very tip of the fold, that's a special kind of point. Well, in geometry, when you're mapping one surface onto another, these ramification points are where things get messy. All the standard rules of translation just break down, and trying to transfer information cleanly becomes a huge challenge.
And this, right here, brings us to the central question that really kicked off all this research. How do you precisely describe what happens to your fundamental geometric data when you move it from one space to another, especially when these messy ramification points are throwing a wrench into everything? Answering that meant they had to build something completely new from the ground up. And that new thing is FUC, Formal Unified Constructs. It's the proposed solution, a totally new language and a whole new set of tools designed specifically to navigate this incredibly complex terrain.
Okay, so here's the crucial idea. FUC is a truly rigorous framework. You can think of it like a set of perfectly interlocking gears. It was designed from day one to govern the precise interactions between those three previously disconnected fields. It's basically the new rulebook that allows spin geometry, ramification, and all those powerful measurement techniques to finally work together in perfect harmony.
You know, before you can build a new language, you first have to define the world it's going to live in. In math, we call that a category, and this one is called SpinKähC. The best way to think of it is as a new mathematical playground. It lays out exactly what kinds of objects are allowed to come in and play, and, most importantly, the strict rules for how they're allowed to interact with each other.
All right, so we've got our playground set up. Now let's open up the toolbox and see what powerful new gadgets we get to use inside it. These are the absolutely essential components of the FCUC toolkit. First up is a tool called the twist bundle. Its entire job is to act like a precision instrument, zeroing in on and perfectly measuring the exact amount of distortion, or defect, that those tricky ramification points introduce. It effectively quantifies the problem, turning what was a fuzzy geometric issue into a concrete mathematical object you can actually work with.
Next up, we have the Ramification Compatibility Condition, or RCC. Now this is the absolute heart of the entire theory. You can think of it as the master equation, or maybe the fundamental rule of grammar in this whole new language. It's this super strict condition that ensures all the different pieces of the puzzle fit together perfectly, guaranteeing consistency when you transfer data, even across those messy ramification points.
Now let's look at the machinery itself. For every single geometric object inside our playground, the FUC framework constructs something called the spinorial complex. This thing is the core engine of the whole system. It takes in all the raw geometric data, the shapes, the spin properties, and then processes it through a very specific set of operations. This complex becomes the raw material used to calculate the final, crucial result.
And here it is, the final output. The FUC invariant. After the spinorial complex does all its processing, this is what it produces. It's a brand new kind of mathematical measurement, what we call an invariant, which is just a special property that doesn't change even when you transform the object. This gives mathematicians a powerful new lens to see deeper into the fundamental structure of these geometric objects than ever before.
So,
What does all this new machinery actually accomplish? And maybe more importantly, where does the research go from here? Let's take a look at what's been achieved and the open roads that are lying ahead.
So the achievements so far are pretty substantial. The framework rigorously establishes that playground SpinKähC as a solid foundation. It defines the RCC, that core mechanism for handling ramification. It successfully constructs the new FUC invariant, and even proves that it's sensitive enough to detect really subtle geometric differences. It even lays the groundwork for more advanced theories. I mean, this is a really solid foundation to build on.
But of course, in math, the work is never really done, is it? A huge goal now is to create an even more perfect universal translation tool, what mathematicians would call a functor. There's also the ambition to extend this entire theory into higher dimensions. And maybe most exciting of all are the potential connections to things like Calabi-Yau manifolds. You know, the incredibly complex, multidimensional shapes that are at the very heart of string theory.
You know, what makes this entire ambitious program even more remarkable is that it's the work of a single, independent researcher. The author of this work is Mohammed Ben Ammar Shraiti. For anyone who wants to dive into the source material, and if you're a math enthusiast, I seriously recommend it, you can find the full research paper using the Digital Object Identifier, or DOI, you see on your screen. It's a real testament to the power of focused, independent research.
And that brings us to our final thought. Building bridges in mathematics is a monumental task. But by creating a shared language for fields that were previously separate, this framework opens up some really tantalizing possibilities. And it leaves us with a question. Could this new approach be one of the keys that helps unlock a much deeper, more unified theory of geometry itself? Only time will tell. Thanks for joining us.